We just calculated the kinetic energy of an electron that was going really fast. It was going almost a little over 1% the speed of light, extremely fast electron, and it was only 56 times 10 to the minus 19 joules. Not a lot of energy. There's a prefix for that. I think it's yocto. I think it would be 5,600 yoctojoules, some prefix that nobody uses, one of those Marx Brothers prefixes. I mean, it's irrelevant. You don't want to use prefixes down in the yocto, zeta, groucho thing. So what you want to do, we need a sort of atomic microscale unit of energy, and we have one. It's called the electron volt. The electron volt is confusing because it's so simple. Okay, so that's what I'm going to have to explain to you. So the electron volt, its definition, it's simply a microscopic unit of energy. Just like a joule. A joule is a macroscopic unit of energy. Electron volt is a microscopic unit. To really see it, what we need to do is go back to electrostatics for a minute. So let's imagine we have an electric field going this way, back to the electric field. That nice direct field. It's easy to think about, relative to the magnetic field at least. And remember, we could draw potential lines along this electric field. And now let's think about a coulomb of charge, the macroscopic amount of charge. Big whopping coulomb sitting right there. And let's think about an electron. Well, now let's make it a proton with a charge of 1e. Right? That's the macroscopic unit of coulombs. The microscopic unit is the elementary charge unit. So coulomb of charge and a proton with 1e of charge. Well, if you just let them go, they're going to fly this way. They're going to go along the field like that. So this must be a high potential, and that's a lower potential. So we're going to call this the 1 volt line and the 0 volt line. Right? If they make it from here to here, they've changed their electrostatic potential by 1 volt. It's gone down by 1 volt, and they've picked up a certain amount of kinetic energy. So we know how to calculate the energy when they get to here. The energy that they pick up would be the kinetic energy. It would just be the charge times the potential difference. Right? It would be a coulomb times a volt. Right? It would be 1 CV, 1 coulomb volt, which is what a joule is. Right? That's equal to a joule. Okay? Now this particle with a charge just of E made this path. It lost some potential energy. It's going to gain kinetic energy. It's the same idea. It's just an electron times a volt. Okay? No, not an electron, an elementary charge unit times a volt. E times V. Or we also call it an EV. Okay? So it's direct. The reason it's sometimes confusing is because it's literally an electron times a volt. Just like a joule is a coulomb times a volt, we just don't give it a fancy name. We just call it an electron volt. So it's not a measure of charge. It's not a measure of potential. It's energy. The conversion factor also can be a little tricky because the conversion factor for joules and electron volts is exactly the same as for coulombs and elementary charge units. 1 EV is a teeny amount of energy. It's 1.6 times 10 to the minus 19 joules. Same conversion factor because they're both going over a volt, just one of them is a coulomb and one of them is an electron. So sometimes when you do problems, you prefer to work in MKS units, but you may occasionally be given a problem where it's microscopic and done in EV. If you want to get back to MKS, maybe calculate a speed in meters per second, you got to convert it, but you've already memorized the conversion factor. It's the same as for elementary charge and coulomb. So we just talked about particle energy, which brings up the interesting question, can the B field, can the magnetic field change the particle's energy? You would think it probably could. First, let's think back to the E field. I remember a problem just like this a little bit ago. Back in LS2. Let's convince ourselves that it's going to get bounced out. So when the electron is here, it has a charge of what? Minus E. So it's going to feel a force, F equals Q. It's going to feel a force back. Because the field is that way, the charge is negative, it's going to get pushed back. So it's going to have some high velocity, but it's going to slow down, and it's going to get pushed and accelerated back, and it's eventually going to come out. Yes, that is right. That is completely relevant. What we had there was a region where the E field points to the right. And we had this little electron here, And when it flies in, like we just remembered, it flies back out. Flies in with some V naught. It has kinetic energy here. When it flies in, the electric field pushes it back. It goes to potential energy here. And then once it's just sitting there, the electric field shoves it out, pushes it out, and it goes back to kinetic energy there. So we had a particle with kinetic energy, and the electric field pushed on it, converted it all to potential, electrostatic potential, and then converted it back to kinetic. So we did change the particle's energy with the E field. Let's look at a similar situation with the B field. So here we have a region where you have a B field pointing into the board, like that. And it looks kind of similar. Let's have particle with some velocity fly into the B field. And we've already talked about what's going to happen. It'll follow a circular path and come out with some velocity, with the same velocity, actually. So let's think about what happens to the particle's energy as it goes through here. Well, it's going through uniform circular motion. The force is always perpendicular to the velocity. So actually, the magnitude of the velocity is constant. So basically, you never lose any kinetic energy. Here, it's all kinetic energy. Here, it's the same kinetic energy. You have your kinetic energy here. You have the same kinetic energy there. You never really took away any of the kinetic energy to make potential, to create some potential energy. So this magnetic field isn't actually doing anything to the energy of the particle. All it's doing is turning it and changing its trajectory. Even though we threw the particle in and it bounced out, it went through the whole process without changing its energy. So if we wanted to make a little rule, we could say that the B field does no work on a charged particle. Now, it's always risky to write things in physics because it's almost always proven untrue. So this is too general to be true. Let's fix it in two ways. A static B field. When a magnetic field changes, that's when you do work. We'll get to that later, to induction. A static magnetic field does no work on a free charged particle. If you're just talking about an electron or a proton flying around in empty space, when you apply the B field, they just go in circles. That's all that happens. So then it won't do any work. We can look at the reason mathematically for a minute. Remember that work, if you want to do work, it's the force dotted with the displacement where you move, and that's the reason it's zero, is you're always displacing perpendicular to your force. That dot product is zero. If you want to take the time derivative and see that a little bit differently, you could say that the power that the magnetic field is doing to the particle is F dot V, if you just wanted to see it in terms of the actual velocity. And we know that the force is always perpendicular to the velocity. So again, the power is zero. It can't do any work. So mathematically, and even in this thought experiment, the magnetic field, the static magnetic field, does not do any work on a free charged particle. Are we sure that the magnetic field can't do work on a charged particle? Because I've seen some pretty crazy stuff happen with magnetic fields and charged particles in my life. And it's a little bit hard to believe that no work is being done. For example, the first way it gets a little bit more complicated is let's have the B field go to the right. Okay, B field that way. Let's put a charged particle in here, Q, and give it a velocity. Let's be crazy and not make it perpendicular to B. Ooh, okay, let's make it be like that. Well, then it's going to have a component forward, call it Vx, and a component up, call it Vy. All right, so Vy is what wants to make it go in a circle. So let's see, V cross B in, the force would be in. And of course, that force's direction will change. That's going to make it want to spiral like this, or go in a circle like this. What about this component? The Vx is just going to drift. So a charged particle in a magnetic field actually usually makes a spiral. It'll kind of do something like that. Okay? But still, there's no work being done. All right? In the plane, it's just going in a circle. There's no work being done as it goes in a circle. It's going at the same speed. In this direction, Vx is constant. If you calculate the total velocity as it goes around this spiral, the speed is not changing. So no work is being done. What if you'd make a magnetic bottle? Magnetic bottle. So what that is if you have two bar magnets, it's pretty easy to make actually. Let's see. The field goes from north to south, so here's south, and you put another one over here. This wouldn't make a very good one, but you could make it this way. So the field lines want to go from north to south, but if you get these really close, like that, it'll go from north to south, and then instead of going around, it'll kind of go like that, and like that. And you'll get this case where you have a non-uniform field. Non-uniform B. So let's think about what a particle would do. Let's draw this a little bit bigger. So here are the field lines where it's far apart, and here are the field lines as they're coming together. And we'll just kind of have them do like that. So here's a more idealistic view of the non-uniform field. Okay? We could have a particle coming in. It's spiraling in. Here it comes. And we got to think about what's going to happen to that particle when it's in the non-uniform region. Okay, so say it gets to here. And we've been thinking it's been going in a circle, but what's really going to happen to this circle? Let's see. So it goes in a circle because, say the particle's right here, and it's spiraling. I forget which way it's going. Oh, it's going up, so the force is out. So it's coming out of the board at you. Okay? Say this thing's coming out of the board. V, if the field were straight, it'd be V cross B. It would go down, right? If it's going into the board, cross B, it'll be pushed down and go this way. Here, the B is actually a slightly different direction. It's, say, into the board, but instead of crossing to the B like that, we cross the B like that, right? So the fact that the field is pointing a little bit this way means the force is actually a little bit back, okay? It's got a component down, but it also has a component x. And that component is pushing against this drift this way. It's going to accelerate it back. And then if it's down here, you do, let's see, so it's coming out of the board at you, V cross B. It's going like this. So the fact that the field is non-uniform as it goes around the circle makes it keep going in a circle in terms of its y force, but it pushes it back. Okay? So what happens actually is that the thing spirals and it bounces back. Okay? And if you have two of them, it's a bottle. The little particles will spiral along the field line, and then the non-uniformity of the field lines will make them come back, and it'll go to this side, and the non-uniformity will make it come back, and it'll go to this side, and back and forth, and back and forth. Surely, the magnetic field is doing work on the particle. It's like a mass on a spring almost. It's just passing it back and forth. It even happens in the real world. If you look at the Earth has a magnetic field. Let's draw the Earth again. There it is, and some stuff out here. Okay, the Earth's magnetic field goes north to south like that. Like that, and it's very tight here at the poles. And it's not so tight as you get farther away. This is a magnetic bottle. Charged particles from space get trapped along these field lines, and here they get really concentrated, and the non-uniformity of the field makes them go back. And then they go down. They're like really fast migratory birds, and then they go back this way like this. Charged particles constantly do that, and when they get here, they interact with the atmosphere and make the auroras. So the aurora you're familiar with is really just particles moving in this magnetic bottle. So it definitely happens, but in the whole process, the magnetic field is not doing any work on the particle. The speed of the particle in this entire complicated trajectory is constant. Now you may say, how could it be constant? Because you're changing the x, right? So this velocity in the x went away, but the velocity around the circle speeds up. It all works out in the end that the speed for this entire process is constant. It doesn't spiral around here and come to a stop and then speed back up. It actually speeds up as it goes through the really tight part to keep the speed through the whole process constant. So the bottom line is, a static B field never does work on a free charge particle. It just can't. It can't. It can't because it always pushes. Its force is always at right angles to the velocity. It just physically can't do work.